Okay, so welcome to day 12 and question 10. I'm actually not going to do part 1 in the video because I think hardly anybody voted for it, and it just involves integrating that equation, substituting in the point x is 4 and y is 8, and using that to find out the value of c, which happens to be 1. I'm going to go straight to part 2, which is one that people have got a little bit confused by, or not too sure how to make sense of this question. And actually, before I do part 2, I want to do a bit of a teaching example of what we're dealing with, because it's probably something that we sort of did really quickly but didn't emphasize as much as we should have. So I'm going to start off by drawing you what's called a cubic. Okay, so let's say this cubic, it goes like this. Okay, so my cubic here cuts the x-axis, let's say, at -2. Let's say it cuts it here at 1 and cuts it here at 3. Okay, actually, to make that look a little bit more to scale, let's make that value -4. Okay, now a little bit about cubics is they are polynomials that have a power of 3. And in this case here, they look pretty similar to quadratics in their factorized form. The equation of this one here, for example, would be x plus 4, x minus 1, x minus 3. Now, you don't need to know about cubics and how they're factorized and all that kind of stuff. Really quickly, see how the x-intercept is -4. That means that when it's in the equation form, it's x plus 4. It's like quadratics where it's the opposite to what's inside the bracket type of idea. Anyway, so if I expand this out, one way I can do that is to leave the x plus 4 out the front, expand out this part here, so x squared minus 3x minus x, which is minus 4x plus 3, and then now go through and multiply out. So I'll get x to the power of 3, I'll get minus 4x squared, but then I'll get plus 4x squared, so it becomes 0x squared. I'll get 3x minus 16x, so minus 13x, and I'll get plus 12. Okay, so that would be a cubic. And you've been asked to differentiate lots of those cubics before. So if we go back to our original curve, though, and have a look at it, we know also a couple of other things about it. We know that we've got some turning points, one there and one there. And that would be, this first one here would be our local maximum, our local minimum, and we know that the gradient at those points would be 0, right? So we already know that the gradient at those points is 0, but we could find those points by differentiating this equation and setting the gradient function to 0 to find out where they are, right? We also know that on this part of the graph, up to that first turning point, the gradients are going to be positive, and that means our function is increasing at that point there. We know that between those two turning points there, the gradients are all negative, which means the function is decreasing. And from this part here to here, we know that the function, the gradient again is positive, so it's back to being increasing. Okay, so you've also been asked questions where you've differentiated and you've used the derivative of the gradient function to find out where the function is increasing or decreasing. So let's go ahead and differentiate it. So dy dx in this case here is going to be x squared minus 13. Okay, which is a quadratic, right? Now, it doesn't mean that the graph you're looking at is a quadratic, but when I look at the gradient function, it will behave like a quadratic. And what that means is this is a positive quadratic, so it'll look like that. Yep. And when we look at this here, we know that this is x squared, the default form of the quadratic, and it's been shifted down by 13. Okay, so here, that point there is going to be -13, and that's going to be that the gradient is -13 at that point. Now, if you look back at the original function here, is there anything on here that can help us go from this to this? Well, let's remind ourselves, we looked before that from here up to the maximum point, the gradient was positive, and then it became negative, and then it became positive again. So this here is the gradient function. Okay, so if I was to sketch this, and each of these values on this curve is the gradient at this point of x. Okay, so if I put my x-axis through there, where it's going to cut the x-axis, that is when the gradient is 0. Okay, so that means that point there and that point there are the stationary values of the curve. Okay, so the stationary values of the curve, you differentiate it, and they will be the same as these values here on my gradient function. Okay, now what this question is asking is, what's the gradient, find the minimum value of the gradient of the curve. Now if I look at this function here, which is a quadratic function, you can see straight away what the minimum value of the gradients possibly can be. It's that value there. Okay, and how would you get the stationary value or the turning point of a quadratic? In normal terms, if we started with this being our y equation, you would differentiate it, you'd set that equal to 0, and then you would use that to find out where that value is. We can do exactly the same thing. So our gradient function is behaving like a quadratic, so we can treat it like a quadratic. Okay, so we can differentiate this, set that equal to 0, and that will tell us where the minimum value of our gradient is. So I'm not sure if that was the best explanation, but I get to try it again anyway now, because I'm going to try it with the actual question, and let's see if I can do a slightly better explanation of it. Okay, so I think I said I wasn't going to do part 1, but actually I am going to quickly write out what you got to at the end of part 1, which was the actual equation of the curve. So the actual equation of the curve was y equals x squared all over 2 minus 4 all over x plus 1, because c was 1. Okay, and we already know, because they gave us it before, that the gradient function is x plus 4 over x squared. Okay, so when they're asking for what's the minimum value of the gradient, they're asking what's the minimum value of the, when they're asking for the minimum value of the gradient of the curve, they're asking what's the minimum value of the gradient function. So this function, however it behaves, let's try and find the minimum value of it. Okay? Okay, so I actually thought I'd show you the graph of the gradient function. So this is the graph of the gradient function here. So it's not a quadratic, it's not something we've seen before, but this is what it looks like. And what they're asking you is to find this minimum value and to confirm that in fact the minimum value is 2. Now you can see visually on the graph that it is 2. We just have to show using calculus and some algebra why it is 2. So no matter what you're looking at, to find the minimum value, you need to find when the rate of change, which is the same as the gradient function, equals 0. I think what's confusing is that because this is we're looking at the gradient function as it's like a function in its own right, you're probably confused about why we're going to differentiate it again and then set that equal to 0, because we don't do that normally with second derivatives. With second derivatives, we're normally using that to find out whether it's a minimum or maximum point. But I guess the idea is here is that you're starting actually at this level. So you're saying, like, this is my curve, this is what it looks like, what is the minimum value of this function? Okay, so at this point, we're going to differentiate it again. So if I differentiate x, I get 1, and if I differentiate 4, x to the power of negative 2, because I would have rewritten that as a negative power, right? When I differentiate that, I'm going to get negative 8 x to the power of negative 3. And you'll see that in the schedule, and then you might be confused why they did that, or you might have been confused about why they then set that equal to 0. Oops. Like so. Okay. So what I'm going to do from here is I'm going to turn this back into a nice whole number power like that. I'm going to move the negative 1 to the other side like that. Then I'm just going to move over here for a second. I'm going to make that negative 8 equals a negative x to the power of 3. And then if you look at that, 8 equals x to the power of 3, and then the third root of 8 is in fact 2. Okay, when they ask you for the minimum value, they're asking you for the minimum value of the gradient. So what is the value of the gradient at that point? So then you would take your x equals 2 value and you'd put it back into this equation here. Okay, and when I substitute x back into that equation, at that point, the gradient at that point is 2 plus 4 over 4 squared, which is 1. So the gradient is 3, which you can see on my graph. That does line up with 3 on the y-axis.